Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR IT, Hyderabad. Today we are going to discuss on diode current equation. So these are the topics which we are going to study today session: current components, and then current equation, diode current equation, and then we will conclude with summary. First of all, before going in detail to derive this current equation, first we need to know the current components of the PN diode. So let us see what are the current components. So before going in detail how to derive the diode current equation, let us know about the current components of the diode. So here the total conventional current is given by I is equal to IPN of X and INP of X. So here we have mentioned diffusion. So what do you mean by diffusion? As I already discussed in the previous sessions, so let me explain you in short. So let us have a p-type material. So in this, the majority charge carriers are positively charged holes, okay, and one side there is a number of majority charge carriers are there, and on another side just less number of majority charge carriers are there. So these majority charge carriers, positively charged same charge carriers, repel each other. When we come across, when these two elements, or you can say these charge carriers when these come to nearer to the one each other, then they repel each other because they are having same polarity, so positive. So due to this, there is a random distribution, like they will repel and they will move away from the particular point. So because of the movement of these positively charged holes, so there is a current. This current is called diffusion current. Okay, so please remember, the diffusion current can be observed in which type of material? So semiconducting materials. Particularly in semiconducting material, we can observe this diffusion type current. Okay, and that too, they are irregular doping concentration. The material which are having irregular doping concentration, so we can observe in that diffusion current. Okay, so what do you mean by this? Is the total current I, and this is IPN. What do you mean by IPN? So IPN, P stands for hole and N stands for N type. So IPN indicates the whole current present in N side. So let us consider this is P type and this is N type material. Okay, so therefore here IPN means what? The whole current, that is, these holes are moved towards this N side. Now the current due to holes in N side is called IPN. Similarly, INP. What do you mean by INP? INP means the electron current. The electron current, because the electrons will move towards the P side, attracted towards the P side, because it is negative and this is positive. So they are attracted towards the P side, and then due to this there is a current flow. That current is called electron current. Electron current due to electrons in P side. Okay, so combination of all these. So what is the variable X? X means what? So this is, for example, junction. Okay, PN junction. So which separates P type material and N type material. So this is X, right? So the concentration, carrier concentration, either electronic carrier concentration or whole carrier concentration will be decreased. So therefore it is exponentially decreased at X is equal to 0. That means exactly at the junction there is a majority of the carrier concentration, more number of carrier concentration. When it reaches or it's moved towards this, so when X increases towards the other end, the carrier concentration will be decreased. Similarly, this is about holes. Similarly, electrons also there. So electrons also similarly will be decreased like this. So this is called total conventional current, diffused current. So diffusion current means which we are not applying under open circuit condition. Under open circuit condition, we can expect this diffusion current, and this is called total current is the diffusion due to holes and electrons. Okay, so combination of these two. So here IPN means current due to the holes in n side as a function of x. As x increases this side or this side, so their carrier concentration will be reduced. Similarly, INP is the current due to electrons in p side as a function of x. At x is equal to 0 at the junction. So I is equal to IPN of 0 plus INP of 0. So IPP again we can also represent the whole current in p side. So there is whole current in p side also. Okay. So that whole current in p side again represented like this. I is equal to IPP of x plus INP of x on p side. I is equal to INN of x plus IPN of x on n side. Okay. So with this knowledge, we can able to derive diode current equation. Let us switch on to the diode current equation derivation. So the total current through the diode can be represented with this expression. I is equal to I naught into e power v by eta Vt minus 1. So where I is the total current flowing through the diode and I naught is the reverse saturation current and V is the applied voltage and eta is the material constant. This eta is material constant whose value may vary for different materials. So it is 1 for germanium and it is 2 for silicon. Okay. And Vt is the volt equivalent of temperature. What is Vt? Volt equivalent of temperature, that means surrounding temperature may affect the diode current. So that is given by Kt by Q. What is K? K is the Boltzmann constant. K is Boltzmann constant. And T is the absolute temperature. It is absolute temperature. And Q is the charge on charge. Okay. So if you solve these values, if you substitute K Boltzmann value and this charge of the electron, then you will have T by 11,600. So if you solve this, for example, at room temperature, room temperature means 273 degrees centigrade. So you will get the volt equivalent of temperature is 26 millivolt. So this is very, very important while calculating the problems. Okay. So how to get this? How to derive the expression for this? I is equal to I naught into e power v by eta Vt. So just now we have seen the current components. So from that we can able to derive this expression. So let us see that. Okay. So before going to derive this current equation, so we need to assume these statements. So depletion width is assumed to be 0. So here the depletion width. So with the assumption of depletion width is 0, and then we can able to derive this expression. Okay. So this depletion means what? So usually there is a p type and n type material. This is the p-n diode. So there is a depletion width between this p and n. Okay. So in general we will have a potential barrier or space charge voltage. So this is given by VB. Okay, we have to take it into consider this VB later. So initially for deriving this diode current equation, we have to assume depletion width assumed to be 0, and then we will follow the next step is forward bias. Okay, under no bias condition and then forward bias condition. Then we have to consider concentration of holes in the n side. What happened to the concentration of holes in n side and p side? then we have to consider the current is small in comparison to the diffusion or drift currents. This is another assumption. And then according to Boltzmann kinetic gas theory, we have to relate this one and this one. What is this? N side. Concentration of holes in N side and concentration of holes in P side. Okay. So then we will consider this low level injection. So before applying forward bias, we have to consider this. So now let us start the derivation. First, what we have to consider according to Boltzmann gas theory. According to Boltzmann gas theory, we can relate Pn and Pp. So Pp is equal to Pn into e power V by Vt. So usually this is Vb. So under open circuit condition, we get where Vb is equals to 0, we consider there is no potential. So second one, depletion width is 0, no? So Vb becomes V0. This is the general equation. Now we have considered under open circuit condition, Pp can be written as Pn into e power V0 by Vt. Okay. So now this is first equation. Now what happens under forward bias condition? Now I am applying forward bias condition. So when forward bias condition is applied, so what happens? So we can observe two things. When forward bias is applied, what happens? What is forward bias? P side is connected to positive of the battery and N side is connected to the negative of the battery. So in such case, what happens? The depletion width will be decreased. Depletion width will be decreased. So, and one more thing is the barrier potential also decreases. The barrier potential also decreases when you apply forward bias to the PN diode. And one more thing is, whatever the holes present in this P side will try to cross the junction and enter into the N region. Similarly, electrons are move and cross the junction and enter into the P side. Okay. Now let us consider only holes. Okay. So let us consider only holes. So the carrier concentration, as I already told you that the carrier concentration will be decreased like this. So this is x is equal to 0. As we move from junction towards the other side, the carrier concentration of the holes will be decreases. So usually we have to consider one terminology. So Pn of x, that means what? So it is the whole current in N side with respect to x. So already we have seen this. Similarly, Pn of 0. Pn of 0 means whole current in P at a junction x is equal to 0. So when we move towards the junction, from junction, so the carrier concentration will be different. So under equilibrium, so without applying any additional voltage, DC voltage, what will be the whole current? Whole current will be Pn0. Pn0 means what? The whole current under equilibrium. This is nothing but under equilibrium. Okay. So now what happens? So when you apply forward bias, the forward bias, then you can observe two things. Electron holes are moved towards the N side. So therefore, what is the state of the holes in N side? They are minority charge carriers. So that means the minority charge carrier concentration will be more, increasing, and the depletion width also decreases. So the movement of electrons or holes will constitute current. Okay. So now what happens? The potential barrier voltage also changes. So therefore, equation 1 can be written as Pp is equal to Pn into e power V0 minus V by Vt. Okay. This is second equation. So what do you understand is? So because barrier voltage also changes. So V0 minus V. So you may get doubt here. So why V minus V0? So because initially we consider initial point. So therefore we have written V0 minus V. So therefore now from equation 1, if you replace this, what is Pp? Pp is Pn into e power V naught by Vt is equals to, and this is Pn into e power V naught by Vt into e power minus V by Vt. So we have separate these, then you will find this. So this side e power V naught by Vt, e power V naught by Vt will be cancels out. Now Pn is equal to, and one more important point here, it is the carrier concentration of the holes in n side will be increased, delta Pn. So we have to add that one also, delta Pn. Delta Pn means what? Excess hole concentration after applying this applied voltage. So delta Pn indicates the excess hole concentration. Excess hole concentration. Okay, this is we have to consider. Now, so what happened here? So Pn is equals to Pn plus delta Pn into e power minus V by Vt. So let us take this left side. So it will be Pn into e power minus V by Vt, sorry, plus V by Vt. So when it come to, it becomes plus V by Vt, Pn plus delta Pn. Okay. So here, so let us take this. So we want to have the expression of delta Pn, excess hole concentration in n side. So that is delta Pn is equals to, we can write Pn into 1 minus e power V by Vt minus 1. So, and this is the second equation. Okay. So therefore, this is what? This is delta Pn. So excess hole concentration present in the n side after applying the voltage V. Therefore, so we can write this. So if you substitute the Pn value, again we have a Pn value here. So if you substitute the Pn value again, so you will get this becomes whole current Ip. This becomes whole current Ip. So which can be written as, so after some time the hole gets saturated. The movement will be get saturated. So therefore it becomes saturated current in the n side. So that can be written as ISP into e power V by Vt minus 1. Similarly, for n electrons also. So for electrons also the same way you can write I suffix n. I suffix n indicates what? The electron current. And this is also ISN into e power V by Vt minus 1. So total current is what? I is equal to IN plus IP, that is equals to, you can simply write ISP plus ISN into e power V by Vt minus 1. Okay. So finally, I can write I is equals to I naught into e power V by Vt minus 1. So this is the equation, final equation. So what is I naught? I naught is the reverse saturation current. Saturation, I told you this is the saturation. After saturation, the hole current or electron current present in the diode. So that is given by ISP plus ISN. Okay. So this is ISN. So therefore, this is the expression. And so we have to consider another point, that is carrier combination, recombination, and also material constant. So we have to consider material constant. So therefore, equation 3 can be written as I is equal to I naught into e power V by eta Vt minus 1. So what is eta? This is the original expression of the diode current equation. So here I is known as total current in the diode, and I naught is the reverse saturation current, and V is the applied voltage. Eta is 1 for germanium and 2 for silicon. Material constant. Eta is nothing but material constant. So This way we have to derive the equation. Today we have studied what are the current components, that is whole current and electronic currents, and then we have derived the expression for diode equation, and the next topic will be capacitance of a diode. Okay, so if time permits, we are going to do some exercise problems on diode current equation in the coming sessions. Right, thank you.